go stepwise. When you work on a metallic, then I think you understand a good bit of the literature. Maybe you already understand it. I think you can reach and convert it and have a smooth and enjoyable. So, key to much of this work or to activate CH bonds, or one of the key concepts to activate CH bonds is really cyclomethylation. So cyclomethylation is a two-step process to make metallocycles. The metallocycle may be stable or not. The underpinning process is to have a metallocycle that is formed. And cyclomethylation, that's why we try to look first at these things. So having to address the CH bond just on its own is very tough, because this bond is one of the strongest ones in each molecule, and it's often buried. So in order to have the metal installed, one of the key principles is to have something out there that guides the metal to the proper place. Cyclomethylation is doing exactly that thing. So in cyclomethylation, you basically have a functional group somewhere in a molecule and the CH bond that can get activated. And then in the presence of a metal, we have in a two-step process, we form a metallocycle that has now a CH bond activated. You see here, there's this carbon metal bond. And then from there on, we can have different events. Either the metal tetraatom bond is not stable, or the metal carbon bond is not really stable, or both are not stable and it's not functional. We'll first look at how we form those metallocycles, and then in the second part, we'll look how we use those metallocycles to get to eventually to those functional bond. So that's what we're doing for today. We'd later get to stages where we don't have that tetraatom that guides the system. So cyclomethylation is quite old. About 50 years ago, the first reports have appeared where palladium has been used for the cyclomethylation of this diaza compound, and you see there's a new cycle formed where the aromatic carbon hydrogen bond has been activated. How can we generate this metallocycles? Generally, the cyclomethylation is a two-step process. In the first process, we have an interaction between the heteroatom or the functional group and the metals. And that can have different strengths. So that's a classic hard-soft acid-base interaction, where a good match between the ligand, donor site, and the metal provide access to this interaction. So too strong an interaction gives us these carbonation compounds that may become totally saturated, and then we have a difficulty to generate a vacant site. Too weak interaction doesn't create any bonding, and we are stuck here. Ideally, we have a bonding that is only partial, so where we have one interaction, but the metal still has a vacant site to react further. And then in a second step, this metal is now close to the CH bond to be activated and can start interacting with this bond and close the metallocyte. And there are two pathways, typically, actually three, to close that metallocyte. These pathways are depending on the number of factors we go through this. Major factor really is, so one is the factor is the nature of the CH bond, and the other is really the metal and its properties. So one pathway is this electrophilic activation, where the metal is the electrophile and the CH bond is electron rich. So we have here the Lewis acid and the CH bond has the Lewis base inside, which marks the interaction. And there are two mechanistic models that have been discussed, and evidence for both have been obtained depending on which metal we're using. One is more an aromatic substitution pathway that you know from organic chemistry, where the electrophile doesn't form the pi complex but straight goes to the sigma complex. We have this iridium, this Wieland intermediate, where the cation charge is distributed in these 5 carbon atoms of the aromatic ring, and this is an sp3 hybridized carbon. And then from here you get rearomatization, loss of the proton, and you can also metallocycle. Yes?
So what is the basic difference between CH activation and CH functionalization?
Between CH activation and CH functionalization. So CH activation, so bond activation is being used in two different contexts. So in one case, we talk about CH activation because we functionalize it. Then it's synonymous. But I think the chemically clear definition of activation is perturbation of the ground state. So activation means putting it into a more active state when it becomes reactive. So we can have so here, for example, the CH bond is activated because it's in a different state than in its ground state. But activation means activation means perturbing it. Some people go as far as calling activation to cleave.
If we want to functionalize it into, we have to do activation.
Yes.
So without activation,
we don't have a functionalization. Exactly. So you need to have the bond activated to be able to functionalize it. In its ground state, it can't. In its ground state, it can't. Maybe I have to just switch on. In its ground state, it can't be activated. In its ground state, it's stable. So activation is required. But then activation has been used in two different meanings. So in one case, activation is, some people call activation whenever you move it out of the ground state into higher energy. Then it's activated. And others use the term activation for cleavage of the bond. So you have activated the CH bond if hydrogen has left. You see both in the literature. People are not totally consistent. Is it on? Charge. I hope did for a moment. Yeah, sometimes you manage. Can you stay there for 4 hours? No, it's not good. Okay, do this. See, now it's good. See, whenever it blinks, it's okay. Yeah, perfect. Done. So, we'll have both. The term bond activation has been used for two different things, or for in the same context for two different events. So that's a bit confusing in the literature. Activation meaning leaving the ground state, activation meaning cleavage. That's not the same, but you see the term used for both, and I would not be confident that I use it only for one. I think I use it as well. This is bond activation, and I mean cleavage. Sometimes I mean bond activation of having just this interaction. Here clearly this is the other pathway. Here we have a CH bond, an agostic CH bond activation, where the metal is agostically bound to the CH side-on binding. So I would call this a bond activation, because now the electronics and the bonding and the geometry and everything in this CH bond is changed. It's moved out of the ground state to an activated part from where it is much easier to cleave the bond. This bond here is very hard, or this bond here is very hard to cleave. It's very stable. Once the metal comes close, the electronics change, the population of the orbitals change, the energy of the orbitals change, now the bond is activated. Now suddenly we have pathways to cleave the bond totally. So I wouldn't say this is the CH activated complex, but this one here. Here the bonds are perturbed. But you see in the literature both. the activated state. That's why we call it activated. So typically, in this state, there's not a long residence time, and the system goes one way or the other. Sometimes we manage to trap it, stabilize it enough that the activated state is cushioned, so we can actually act another. We'll see cases in crystal structures of this, where clearly all has been activated or is activated, but stable enough to isolate. But typically, you can add any type of pH that it reacts while this one here is not activated in the liver.
This mechanism, transition stream, there is this one here intermediate.
So this one, yeah, well, yes, this is an intermediate. This one is typically a transition state, but you will see that depending on the metal and depending on the ligand, we can stabilize. So there's not one is a transition state, the other is an intermediate, but depending on the metal and the system we're using, the stability changes. So in some compounds, this is a transition state, and in others it's an intermediate. So you see that the energy profile for this reaction, so I abbreviate this. The energy profile of this reaction is we get the activation and then we have some a stable, and then maybe 2 or 3 intermediates here that may be short or long lived depending what energy you're having. But that's only for one metal. If we have another metal and a slightly other carbon, it may be that now profile looks like this. The reaction coordinate is still the same. If this is the reaction coordinate, so the progress of the reaction. But you see, this one here is an intermediate at this stage of the reaction. Well, for this metal, it's a transition step, and the other way around. Here we're close to an intermediate. Oh, here we are at the intermediate stage. While for this one here it's a transition. So with this carbon, with the white carbon metal combination, we're unable to stabilize and see geometry and the situation of that reaction coordinate point. But with the blue one, we are. So it really depends there which metal we're having. It may be a different place where we can arrest the reaction, but they all follow more or less the same coordinate. So change the system, and you're suddenly seeing some other insights, and in the end, if we put this all in a row, we have a very detailed view of the whole process. And that's what we want basically in these cyclometalations. Because this has been studied now for 50 years, still there's more to discover, but I think we have now a bit. So that's two possibilities, and you see in this agnostic interaction, only the CH bond is really interplaying, and the rest of the aromatic ring doesn't get massively perturbed. While here, of course, the electronics of the backbone are perturbed. Still, some concepts clear. If either the ring or the CH bond has to be electron rich, so we know what type of substituents are accelerate this reaction and what substituents decelerate the reaction. If the metal is electrophilic, we want to have an electron-rich CH bond or electron-rich carbon here, so the more donating groups, the faster the reaction. The second principle for activating this bond is opposite, if you like, because it's an oxidative addition. So where this CH bond is oxidatively added, we get the cis interaction, because the oxidative addition has to be cis. It is homolytic cleavage. maybe or not, reductive elimination occurs, and then we get the same mechanical cycle that I've shown you through electrophilic analysis. And again, this is all due to the you know why this has to be sigma bonding, pi back bonding, that's you're familiar with, yeah? Or do I draw it? And then the third mechanism we see is the so-called sigma bond metathesis, which happens, which is kind of a disproportionation reaction, if you like, where the metal where the metal and the ligand interact simultaneously with the CH bond. But if you like, dipolar or dipolar interaction, so the ligand interacts with the hydrogen and the metal interacts with the carbon. And you see these are opposite interactions. The carbon is Lewis basic and interacts and induces a polarization of the CH bond. The metal is Lewis acid and contributes to the same polarization of the bond. This is, from an electronic point, very similar to what we discussed in the outer sphere transfer hydrogenation process, where opposite polarities induce a polarization of the substrate. And here we have a four-membered transition state, which can fall back either side, but typically the ligand here on the metal precursor is something that is a very strong base. And once it's protonated, it's becoming such a weak acid that this part here is irreversible. Well, this part here obviously is reversible. So we form something that is super stable. This could be a metal hydride we form by hydrogen. It could be an alkyl complex, so we form an alkane, which is very hard to inactivate. It could be an AMH or a hydroxy alkoxy compound, which is then a bit more acidic and still provides a signal. In some cases, especially with late transition metals like ruthenium, it has been shown recently that the metal does not only interact with the ligand and the carbon, but also assists the proton shuttling. That's then called a complex assisted sigma bond metathesis, a CAM mechanism. Robin Perutz and Sylvie Subway here promoting this. But that's a very special case. It's essentially the same. Well, no, it's an assisted process, but it falls over the same. So what decides whether we get cyclomethylation and what type of cyclomethylation? And there's basically 5 factors we have to consider. We have to consider the coordination ability of the coordinating site. We have to consider the nature of the metal center. We have to consider potential roles of X in assisting or not assisting cyclomethylation. We have to consider what forms stable products, or if you like, what transition states are low-lying and then lead to stable products. And then, of course, a key factor also is the reactivity of the seed. Go ahead. Can I come there? Yes. Yes.
This is auxiliary.
Yes.
How do we distinguish between?
Very good question. If you just look at geometries, it's almost impossible to say whether you arrest an agnostic interaction or an electrophilic cluster. So what you can see is calculations help you. Because calculations can tell you a bit where should the electron density be. Because this one here is a 3 center 2 electron interaction. This one here is a 3 center 4 electron interaction. So it's their orbital population can help you. Intuition just. As oxidative tissue is rarely molded here. But this is exactly, or this is a very important point because the reaction coordinate looks almost the same. You go from an agnostic interaction to the CH activation. Now this one, clearly, if you end up at that stage, you have done an oxidative addition. Whatever it is, this is an oxidative addition. An electrophilic substitution will never ever go to an oxidative addition. Then the proton will be abstracted differently. But so we should see as we go through the intermediates, we should be able to distinguish the different pieces. But in terms of just the reaction coordinates, they look exactly the same. So this is like the sigma complex that will then start the oxidative addition.
Experimentally it is not so easy.
No. And the easiest way to distinguish what you get is by looking, and coming into this is by looking at the role of the reactivity of the CH bond. So if we start to have here an electronically active group, we should see different rates whether we pump electron density into the CH bond or whether we remove. And that is then, for me, the most compelling case to say, it's electrophilic or nucleophilic. Because basically, in the electrophilic substitute activation, here we pump electron density from the CH bond into the metal. This is a donating interaction. The sigma bond gives electron density to the metal. At 3 center, 2 electrons. The only 2 electrons involved are the CH bonding electrons. So the more we push electron density into this ring, the faster the reaction. So that will help me to distinguish, yes, it's electrophilic. In oxidative addition, it's the inverse. We pump electron density from the metal into the CH bond. And then we see. So experimentally, this will be, I think, the most compelling way to distinguish this oxidative addition. And in sigma bond catalysis, it's neither or. We're having 4 center 4 electrons. It's a metathesis. Sigma bonds, we just flip them over. So as a consequence, this is not so dependent on electrophilic, on substitution patterns of the aromatic ring. Because it doesn't matter whether it's electron rich or electron poor, it has to match the metal burning alignment. So I'd say once we understand those 5 factors, this is a fairly simple list to understand. So for a chemical reaction, I think this is very okay. We have just 5 points that we have to discuss and consider, and then we know the link. And it's amazing, we can really predict almost everything. The most spectacular oxidation transformations from those guys. It's okay, it all fits, it all makes sense. To the point that the actual chemistry almost becomes trivial. So the ingenious part is what functional group it is. So I'd like to go through those 5 points quickly. I hope you can memorize one or the other. But if you know those 5 points, you understand most of aromatic, well, most of CH functional, etc. That's it. So coordination ability of the donor group, point 1. That's really a hard soft acid base. And we have clear-cut separations, early transition methods. They like, of course, large donors, so oxygen functional groups are preferred, carboxylates, peroxides, alcohols, ethers, very good. For late transition metals, we'd like to go softer, so phosphines, thioethers are particularly good. With amines, imines, so you know the hard soft acid base sequence. So phosphines and sulfides from 3sp, from the 3rd row are constructed, and from the 2nd row, the more we go to the middle, soften the inside. And then we have hybridization, sp hybridized are softer than sp2 are softer than sp2. So amines are harder than imines are harder than hydrogens. And the same holds for oxygens. So ketones are harder than are softer than alcohols. Alcohols or alkoxides are softer than oxygen. And then the bonding plays a role. So for example, if we start from an amine with palladium acetate, we get in an electrophilic activation this metallocycle. If we add then an imine, the imine can displace the amine, and we eventually get a transcyclization, and we get the CH activation of this bond here to form that compound. So this is in an equilibrium, and the equilibrium is driven by the softness of that nitrogen compared to the relative hardness of that amine.
For assistant, I would rather prefer the CMP mechanism, cyclometer reciprocal base assistant.
I mean, for the cyclomethylation, the base, yes. So for this, we'd like to have the cyclomethylation basis. Yes. For the cyclomethylation, we need to have both. We have to show the proton, but then there are two mechanisms for this reaction. And in this case here, it's dissociative, but we have as well found other cases where it's associative. So you can imagine two possibilities here. That dimer we start, we cleave initially the dimer. So that's the pyridyl carbon. The acetate is there, helps. We have an intermediate where the two are together. We form and now the acetate protonates this guy here. So then this is all microscopically reversed, so we have an equilibrium. The equilibrium is driven by the coordination of, sorry, I forgot there. That would be the isomerization edit. So that's the associative mechanism, I will call it, where we have at some point two metallocycles that interconverge. The other mechanism is that first, comes into the play, cleaves the bond, so basically what I showed on the cyclomethylation just in the reversible way. And then we have competition between that nitrogen and nitrogen to coordinate the palladium acetate and eventually get on. So that I would call a dissociative mechanism. In both cases, we have acetate here, and we form more acetate in the reaction of can you see this? So you form more acetate from this reaction, you form back the CH bond, which is acetate. So for the transact pincer ligands are, I'll try to be quick on the pincer ligands. Pincer ligands are interesting because they have two different, or two coordination sites on the same molecule. This imparts extreme robustness to the metal carbon. Because now the metal carbon bond is internally stabilized. The metal carbon bond is now really buried. You need to cleave first the coordination bonds to access the metal carbon bond with any insertion. So that imparts a very high stability and leaves organometallic chemistry basically back to organic chemistry. You can bond the compounds, you can boil them in HCl, you can do many things that typically metal carbon bond will survive. So that's interesting on its own as for the metal carbon bond as an entity for further functionalization, for immobilization, for whatever you want to do. Then this double coordination can cause some specific reactivities. For example, if the metal and the ligand are a bit in a mismatch, so you have hard hydrogen and the soft palladium, chelation is not so stable, and you typically get cyclometallation at the outer side because one palladium coordinates to the nitrogen, and then this position here is sterilely hindered, and cyclometallation won't take place here without something. Only if you activate the carbon bond, like in a carbon-silicon bond, the silicon is an activator, like from what's it called? Gamma coupling. You actually use the silicon as a cleavage agent. Then you can direct the metallation to that side. This is different when you have phosphines, so they can match. Hard soft acid base matches much better. So if you add a metal precursor, you initially get some polymers or dimers, but eventually you get these type of chelating structures. And now the metal is very close to the CH bond. And so you get cyclometallation very easily. Same holds for sulfurs, where chelation is very good. Then with early transition metals, obviously you get, you have harder metals, so you'd like to have oxidolars to direct the cyclometallation. Now, here we already start the second aspect, so we looked at what is the nature of the donor group, then the second point is what is the nature of the metal. Early transition metals having no d electrons or very few d electrons, they're very generally undergoing sigma bond metathesis. So here you see tantalum, this is tantalum 5. 5 anionic ligands are alkyls like methyl or benzyl. So this tantalum 5 has a D0 electron count. The classic mechanism is a sigma bond metathesis reaction. And you see here in sp3 carbon gets activated, so this CH3 is very close to the tantalum R group, like here this methyl group, and you get a transfer. You get a transfer of the proton to the R, and at the same time this tertiary butyl methyl group gets activated. This then tilts the phenol on one side, so the other tertiary butyl group cannot enter. And so early transition metals, high valent transition metals, typically generally undergo sigma bond metathesis. Very electron rich metals traditionally undergo oxidative additions, and the prototypes are iridium-1 and rhodium-1, palladium-0, but we do not want platinum-0. So really high electron count, D8, D10. Now we have to be careful with D8 because iridium, rhodium, D8 is nucleophilic, palladium and platinum, D8 is electrophilic. So it's not just the counting of the number of d electrons, it's also which group they belong to. Palladium plus must be electrophilic, otherwise we wouldn't be able to account for all the cross-coupling things that we're seeing. The easy reduction to palladium 0, analytic substitutions which dwell on the electrophilicity of the palladium 2. Same holds for iridium 3, rhodium 3, very genuinely electrophilic, that's the plan. We have a a few systems then that are borderline. Ruthenium-2, we have seen for ruthenium-2 both electrophilic pathways and nucleophilic pathways. With the nucleophilic pathways, we're not sure whether there's a transient reduction to ruthenium-0, which of course makes it very important. And then iron or nickel are again borderlines. Sometimes we see signs or the characteristics of nucleophilic, sometimes electrophilic substitution. So then here the ligands, the donor properties of the functional group, etc. may play a subtle role in directing the course of the reaction. And then of course, when we get this ambiguity that you mentioned, that the reaction coordinate is almost the same. It's very interesting for those. But as I said, most of the ruthenium-2 is similar to iridium-3, rhodium-3, electrophilic. Some evidence shows as well. So here's the classic oxidative addition, reductive elimination pathway where you have a phosphine that is a very good match for iridium-1. Iridium-1 is very nucleophilic, very strong donor, very electron rich. So once the phosphine is coordinating, these CH bonds get very close. And here, maybe because of the high affinity of iridium-1 for olefins, for back bonding, we don't get this CH bond, which is actually more acidic than these ones at the back activated. You get those ones at the back activated, and before these are normal terpenes. This is not work by us, but it's interesting. Then we see here one of the advantages of the spin ligands, because they're so composite, they always be resistant.
Sir, first iridium-1 and rhodium-1, they favor agastic interaction or oxidative addition. So we just discussed when they are just opposite.
Yes, because, well, the actual interaction is the same. But one goes then via an electrophilic bond cleavage, and the other one goes via a back donation. So at this stage, we have no clue to distinguish. So I should have been maybe a bit clearer. At this stage here, there is no sign that tells us this is an electrophilic or a nucleophilic activation, because the interaction is the same. This is, as an apostolic compound, this is a 3-center 2-electronic interaction. At this stage, you cannot distinguish. Yeah? This interaction is sigma bond that is interacting with an empty d orbital at the metal. So this interaction is a ligand to metal charge transfer. 2 electrons, 3 centers. In both cases. The question is what happens from there. In an oxidative addition, we have backbone. In an oxidative addition, the sigma star orbital of the CH bond gets populated by the d orbital, by the filled d orbital of the metal. So now we have two other electrons that start to interact with the CH bond. So in total we have 4 electrons that start to interact with the CHN triangle. So we put the electron, there's more electron density in the ring, in this construction, and so we have an oxidative addition. This cleaves, and we form 2 new bonds. If the charge transfer is complete, we get 2 new bonds. This is the oxidative part. We transfer the 2 electrons from the metal into the CH construct to form 2 new bonds. So here, if you'd like to have this of course we can't label the electrodes, but maybe for instructive use, we have transferred 2 electrons from the metal into the ligands, because the ligands are 4 ligands into the ion. So that's the oxidative addition. For the electrophilic activation, now we remove the proton. This here polarizes the CH bond, because so that's sigma donation, that's pi back bonding. Yeah. So here we deplete the CH bond and make the hydrogen very susceptible to be captured. For sake of thing, I take another nucleophile, maybe a base. That could be a chloride, that could be an acetate, that could be whatever that is there in solution. It's the base. So with this interaction, we make both here more electropositive, because they remove there's less electron density. So here, the electrons stem from the metal. Here, the new electrons stem from an external additive. So what you then get is something of that kind as the next transition state, where electrons are taken from an external into the proton, which directs the other electrons into the metal carbon bond. So that's electron.
And the electronic nature of the metal is same for both the processes.
Right?
The electronic nature of the metal, can it be same for both the processes?
No.
But
because for this process, the electronic configuration at the metal needs to have those electrons. Here, these electrons are not available for this reaction. And so what do you mean, whether it can be D8 or D8?
then you have a high electron density, that is nucleophilic, favors agnostic or oxidative.
Yes. Yes. So high. Okay. So remove the acoustic interaction from that. Acoustic interactions are in most cases happening, but then they favor oxidative addition. So the acoustic interaction is required in most cases. So if acoustic interaction is not a distinction between the two. So yes, so this should be the acoustic interaction should be created here, or it should be added here. So the acoustic interaction is really that's the initial interaction. That's, if you like, this is the activation of the CH1. That's where we move it out of its comfort zone. So just quickly, let me break up. There's two, so with rhodium here, you see there's the acoustic interaction that we can stabilize in these pincer compounds. You see here a crystal structure where the rhodium is very close to the carbon and the hydrogen. So here we have this transition state kind of stabilized. And then we have palladium compounds that are very similar. You see that the construction is almost the same. We have here this carbon that is almost sp3 hybridized because it interacts both with the hydrogen and the rhodium. And here we have the same, but here the platinum is really far away, so this is a totally tetrahedral carbon. From the crystal structure, the platinum is far away from this carbon. So here we have a aromatic substitution type system, and we see this also in the bonding interaction. So if we have here a functional group, we see double bond localization. So in one case we have more of an aromatic substitution intermediate that we stabilize, and the other one we arrested at the CH bond, and you see this is a consequence of the whole different electronic configuration, rhodium plus phosphines and the carbonyl, and here platinum, a donor group and hydrogen. So by changing here and there a parameter, we can potentially stop the reaction.